I don't know who thought this was a good idea, but it does seem to be working. Welcome back to Cloud 42. I'm James. About 4 months ago, I made a video about turning a Noga big boy articulating arm into a camera mount. That was the video where I used my tool post grinder with a thread mill to cut threads in 4140 steel. I got two kinds of comments on that video. One, that the thread milling was totally gratuitous, and two, that it wouldn't work because vibration from the machine would spoil the shot no matter how rigid the arm was. That second criticism would be true if I were planning to stick the magnet to the machine. But the plan all along was to stick it to magnetic surfaces near the machines, which of course don't exist. So today, we're going to make them exist. I think the ideal target to stick the magnetic base of the Noga big boy arm to is going to be a circular steel plate about 5 inches in diameter. I want to make it circular so that I can mount the magnet in any orientation I want. That will allow me to align the length of the magnet with the direction that the arm's sticking out to maximize its moment arm, maximize the torque that it can take before it separates from the plate. If you stick the arm out sideways across the narrow width of the magnet, it can resist a lot less torque before it breaks free. Now, I'd love to just attach these to the underside of cabinets or to the ceiling of my shop, but the ceiling is too high and I have no cabinets in the right places, so we're going to need to extend some kind of a support down from the ceiling. And the material I want to use for that is called Unistrut. If you've never worked with this stuff, it's a folded sheet metal product, 1 5/8 in width, and it has an open channel with these little hooks so you can slide in captive nuts and then run bolts through into those nuts to bolt this stuff together. And this is like an industrial erector or Meccano set, so you can just cut this stuff to the appropriate length, bolt it to walls, bolt it together, and use it to hang conduit, HVAC equipment, and other kinds of applications in an industrial environment. Now this stuff comes with all kinds of parts. This part here is a standard part called a post base, and it's normally used to set on concrete, run anchors through the 4 holes, and give you a way to insert a piece of strut that comes up from the floor to support a piece of equipment. I'm going to do exactly the opposite. I'm going to bolt it into a couple of pieces of unistrut on the ceiling and use it to create a down rod to come down to where I want to mount the plate. Now I can't mount this directly to my ceiling because there's no structure, it's just drywall with joists or beams on 24-inch centers. So I'll use a couple of more pieces of unistrut to span across those, and I'll drill small holes in it 24 inches apart for screws to attach this to the ceiling. To attach it to the ceiling, I'm going to use what are called structural connector screws. If you haven't seen these are really neat. These are designed for use in wood frame construction. They come in all sizes and all lengths, and this is a hardened steel screw that's intended to be weight bearing for like attaching hurricane brackets and joist hangers and other kinds of structural connector components in a wood frame building. It's hardened steel, it has an aggressive thread, and you can see there are teeth cut in the end of it so that it will cut the wood fibers when it goes in instead of spreading them, reducing the tendency to split, and then it has a built-in washer head to spread the load across a sheet metal bracket, which is exactly what we have here. The head is small enough it would fit through these large slots, but if I just drill some small holes, 1/4 inch, maybe a little bit bigger, then those screws will go right through and that washer head will grip this and hold it tight to the ceiling. Now for the mounting plate at the bottom, I could just use another one of these post bases. The problem is this material's relatively thin. It's about 5 millimeters, and this is a weldment, so there's a weld bead around the bracket here. And every single one of these that I've seen is warped, and warped significantly. So a magnet is not going to stick to this without trying to flatten it out or machine it. These things are galvanized. There's not much material here to remove, so I think that's a dry hole. Instead, I'm going to make my own plates. I'm just going to cut a circle out of 1/4 inch steel plate. I've got a bunch of A36 laying around here in the shop. And then I will cut 3 more pieces for a mounting surface and a couple of side wings to support it, and we'll just weld this together. To cut these out, I'm going to use my CNC plasma table, so I just inserted duplicates of all of these parts into the model. These are just, you copy and paste in Fusion and it makes a duplicate that's referenced. So if you modify the original, it modifies the copy as well. And then we'll just come over here into the manufacturer workspace, and I've already created a setup with a profiling operation to just cut these out with the plasma torch. I'm using my Hypertherm 30XP, and the standard consumables give a 50 thou kerf width. So I've just sort of laid this out with reasonable looking parameters, and we'll go slice them out. Now I've already cut a couple of these just playing with it and trying to get the parameters figured out. And it turns out that with the Hypertherm 30XP on 30 amps on this particular plate with the standard consumables, 20 inches a minute gives a nice clean cut. So that's what we're going to use. Let's go cut some of these out. This is my Langmuir Crossfire plasma table. You saw me build this in a previous video. This is set up with a Hypertherm PowerMax 30XP plasma cutter. Now, this particular plasma cutter is not really intended for machine duty. It just has a hand torch. In fact, the torch is permanently attached to the plasma cutter, so you can't even install a machine torch on it. But you can buy the machine torch consumables. And you can see that I have a CNC machine torch shield on here instead of the normal drag shield that comes with the machine. Now, as these parts are severed, some of them kind of fall and tip up, so I'm kind of reaching in with the hammer and knocking them out of the way just so the torch doesn't strike them as it comes around the perimeter of adjacent parts. This plasma cutter did a beautiful job and made short work of this. The 20 inches a minute is fairly slow, and it does risk running into the duty cycle limitation of the machine. This particular machine, I think, is only rated for 30 or 35% duty cycle at 30 amps. However, because it's late in the fall and it's cold outside, I'm getting a lot more out of it. I've got the plasma cutter sitting right at the open door of the shop, so it's sucking in outside air that's just a few degrees above freezing. And under those conditions, this thing is cycling the fan on and off in the middle of a cut. So clearly it's able to keep up with the cooling system, and I'll bet I could run this thing with 100% duty cycle under these conditions. There's very little dross on these parts, but what little there is comes off quickly and easily with a 2-inch roll-lock flap disc on a right-angle die grinder. Just one swipe over the edge knocks all of it off and leaves a nice little bevel. When I was trying to cut these faster, it was leaving quite a bit more dross and a lot more of a tapered cut. The manual calls for a maximum speed of 40 inches per minute for a 1/4-inch steel plate with this particular plasma cutter, but that's way too fast. 20 inches per minute I found to be kind of the sweet spot between productivity and getting a relatively square cut with relatively little dross. I've also tried deburring these on the Scotch-Brite wheel on the buffer, and normally that works pretty well, but the edge that's left on these is very, very hard and very sharp, and it tends to just tear up the wheel. So you go through a lot of wheel really fast, and it doesn't do nearly as nice a job as this little flap disc. So that makes this my go-to process. Oh, and by the way, this little die grinder can run way too fast for these flap discs. So you can see I've got it on setting number 2, so it's running relatively slow. And of course, the other advantage of that is that it's quite a bit quieter. Now that all the parts are deburred, it's time to weld. I'm going to use a right angle fixture here on my welding table to make sure that all of this is square, and I'll use my Fireball tool spacer blocks here just to make sure that everything is the right distance apart. And this will give me a nice repeatable way to set this up. I'll just use these parts to make sure everything is flush while I clamp it in position, and then I'll set the side brackets in place using the magnets. At least I'll use the magnets on this side. On the other side, there are no magnets, so I'll get the parts lined up and put a can't twist clamp around this to hold everything in position while I weld. The advantage of using a fixture table and setting up a fixture like this is instead of just sort of putting things together, tacking them and tapping them, I can repeat this for the other parts. Now, avoiding distortion is kind of the name of the game here, so I'm just making short stitch welds. There's no reason to weld these up fully. This is not going to bear a ton of weight. It's just to hold the plate and make it rigid, so these short stitches or glorified tacks will be plenty to hold this together. Still kind of experimenting to see how much heat we need here, and looks like we've got full penetration. This should be just fine. We'll get the other 3 of them welded up here, and we should be ready to attach the round plates. Now, there's nothing here that needs to be particularly precise, so I'm just using a scale to line these up and try to get it more or less centered. This is really just a visual thing. If it looks centered, it is centered. Use a clamp to hold this down, just to keep this nice and flat. And once again, the biggest threat here is that this base is going to warp. So I'll just make some nice short little stitch welds and not try to weld this up completely. I am gambling that I can make these a little bit longer than the stitches I had on the side just for strength without unduly warping the base, but we'll have to see how that turns out. These look good. They look solid. I don't think we're going to have any trouble with this. How flat is it? Okay, it's not that warped. I've got a little bead of weld spatter under there or something. Checking this with a scale, I'm just eyeballing this, and I'm betting that if we take 10 thou off of this with a fly cutter, it'll clean up nice and flat. I'll get the other 3 of these welded, and I'll meet you over at the mill. To flatten these, I'm going to use a fly cutter. This is the Tormach SuperFly, and I'm using the polished insert that's intended for aluminum. And then I have a fixture here in the vise with a couple of threaded holes to match the holes in the bracket. So I can mount this, we'll level it up, and then take some skim passes off the top. Now, because I'm using the polished insert for aluminum and it has a very sharp edge, the cutting forces should be relatively low. So I should be able to get away with this setup, even though it is going to be pretty springy and singy, and it's going to make a racket. I do need to get the plate as close to level as possible to minimize the amount of material I have to take off. So I'll just use a dial test indicator, and I'll average the readings on opposite sides and try to even it up. I can just sort of tap it here, and the block will slide in the vise. And then to tilt it front to back, I can loosen the bolts just slightly, and I can tap and take advantage of the free play in those bolt holes and kind of level it up in this direction. And I just keep working this until eventually it's close enough. The plate isn't flat. That's the whole point of this. So it's never going to be perfect. But if I average the readings on opposite sides until I get them about the same, then I can minimize the amount of material that has to come off to clean up the part. Now, to get my initial cut height, I'm just going to spin it up and touch off on the part. And you can already hear how this is going to go. I just raised the knee 5/1000ths of an inch, and we'll go ahead and take a pass across here and just see how we do. I'm hand cranking these first couple passes because I'm not quite sure how they're going to respond. You can hear the plates ringing. There's quite a bit of flexibility here, but honestly, the surface finish is pretty good considering, and I think that's because of the sharp insert. That was 5 thou. We'll take 5 thou more and see if this cleans up. You can see I'm running the power feed now, and this allows me to kind of tweak the spindle speed versus the feed speed to sort of try to find a minimum of ringing. And it looks like 10 thou is indeed going to clean up this plate. Oh, and if you're wondering why I have sheets of laminate flooring underlayment taped up around the mill, you've clearly never used a SuperFly. This thing makes the biggest mess I have ever seen. Well, the plate seems flat, the magnet seems to stick, and honestly, the surface finish is quite a bit better than I was expecting. I thought I might have to use some machinist jacks to make this more rigid, but it looks like it turned out okay. Let's do the other 3. With the plates and brackets welded and machined, it's now time to cut the strut to length. I found that the quickest and easiest way to do this is with a cold saw. This stuff is pretty hard to cut on a bandsaw just because the walls are so thin and it tends to grab the teeth of the bandsaw blade unless you have a very fine blade. Hacksaw doesn't sound like any fun, but one of these cold cut saws just goes through it like butter. Now, of course, the downside of a saw like this is that it throws chips everywhere. That's why I'm working on the floor and I'm working over against the garage door. I'm just trying to contain the mess because these chips come off hot, they come off blue, and they go everywhere. Did I mention that? I think if you had a hot work shop that was already pretty messy, a tool like this would fit right in, but in a machine shop setup like I have where everything is relatively neat and clean, this tool is kind of the outlier. It just throws stuff everywhere. Oh, and maybe the SuperFly, that throws stuff everywhere too. And if you're wondering why I'm wearing shorts, it's because I'm actually cutting these parts between sets working out here in the gym. Parts do come off nice and cool though. Oh, there's my timer. Time to squat. With the pieces of strut cut, we need to drill the holes to mount it to the ceiling. I need the holes spaced in the center between the webs, and I don't really want to rely on the cut ends for placement just because I just cut those off with a tape measure and a Sharpie mark on the cold saw. So what I want to do is reference off of the slot. So I've got a 1, 2, 3 block down here and a mill table stop bolted to that, and that clamped to the table. And that gives me a rod I can use to reference off of the inside of one of these slots. So I can just set it against that slot, drill the hole in one end, then I can easily just pop this out of the vise, flip it around, register it on another hole, and drill the hole in the other end. And this way the holes will be centered, they'll be repeatable, and even if the cuts on the end aren't exactly right, it'll still line up. So I'll just use an edge finder to find the front and back vice jaws, use the half function on the DRO to find the center, then do exactly the same thing between these two slots. That'll locate the center of the web, and we'll just grab a drill and push it through. Nice and easy. Do you need a milling machine to do this? Of course not, but we have one, so we're going to use it. So now we can just pull it out, flip it around, put it in about the right position, register it up on a slot, and we should be ready to drill the second hole. Repeat this 8 times, and we'll have all of the pieces of strut for the ceiling finished. Is this overkill? Of course. What's your point? Now, the last thing I want to do is assemble these things overhead on the ceiling. So I'm going to use my welding fixture table. Got the parts cut, and I'll just use these pegs in the table to align them and clamp them in position. Now I know how far apart these need to be for the post bases to fit. I do need some extra 1/4-inch shims here to get the right spacing between the struts, but this will ensure that they are aligned, they're square, they're parallel, and the ends meet up. And so they'll mount securely to the ceiling and the holes will line up with the joists. Now the nuts that work with this just twist into place and are held in place by a spring. This allows you to position these nuts anywhere along the strut. Once those are in position, I will just secure these down. You can get these with all different sizes of hardware. I opted for the 1/2-inch nuts. And then the bolts I just bought at a local farm store that sells grade 2 hardware for $3 a pound, which is like the greatest deal ever. These bolts would be over $1 a piece from my local hardware store. And I got a great big bag of them. Everything for this project for 15 bucks. So that is absolutely the way to go. So with these torqued down, I know that this is square. I know that everything's aligned and this is ready to go onto the ceiling. Just need to assemble the other 3. I do actually want to make sure I get these screws driven into the trusses in the ceiling. So I'll use a stud finder here to locate exactly where they are and mark it. I've already measured and I know they're 24 inches on center. So as long as I can find one, I know where the others are. Now to hold the weight of this while I'm working, I just have it sitting here on a C-stand and I'll just extend this up to press it against the ceiling. And that will hold it in place while I work, so I don't have to support the ever-increasing weight of these parts over my head. Now, these structural screws just go straight in with very little trouble. They are Torx drive, I believe they're a T30, so there's very little slippage, and they go in very, very easily with a little impact driver. And with all 4 of those in, we can take away the C-stand, and that is permanently attached to the ceiling. I've already got the nuts into the down rod, so we'll go ahead and mount that. Just 2 1/2-inch bolts with washers, and we'll tighten those down. And the thing about this strut is there's always a little bit of play, so it's really easy to make little minor adjustments. I'll probably come back later with a level and make sure this is perfectly vertical, but for now this will do. That attached to the ceiling, we can now attach the plate to the bottom, and it's the same deal. I've got the little spring nuts in there, and we'll tighten it down with 2 1/2-inch bolts. And of course, there's plenty of adjustability here too, so I might come back with a level and make it nice and neat. You know I'm going to come back with a level. Seems pretty good. Let me go grab the magnet and a camera and let's give it a test. Now I intentionally set these plates about 6 inches above the top of my head just to try to avoid personal injury, and it looks like that height is going to be about right. And it looks like the magnet does indeed grab pretty solidly. If I pull it to the side, I can break it free, but pulling in the direction of the magnet, it seems much, much more rigid. Yeah, there's no way this is going to get pulled off accidentally. In fact, I got to keep tightening this to even get it to come off at all. That was a lot of force. There is no way that is ever going to happen with a camera. Let's try it with a camera. Now I've got my camera set up with plates on the bottom and on the top, so I can mount it either way, and the top plate is really the most convenient way to mount it with these overhead mounts. Looks like I've got plenty of reach to get in nice and close, especially with the zoom lens on the camera. Feels nice and rigid. There's a little bit of springiness, but it damps out pretty quick. It's certainly more rigid than the C-stands I've been using, and vibration in the mill doesn't transmit to the camera at all. Looks like it will reach far enough to get a nice wide shot as well, and yeah, that's not going to come off on its own. I think this is going to be great. Now, admittedly, this is a pretty large camera, and you may be thinking to yourself, James, I want to make videos, but my camera's not that big. Well, it's not really about the size of the camera, it's about how you use it. And many people live full and complete lives and even make great videos with a small camera. Or so I'm told. I'm pretty excited to have this. You may not know this, but if you use a tripod to hold your camera, it's virtually guaranteed that you will need to move the mill during a shot and a tripod leg will be in the way of the knee crank. I think it must just be a fundamental law of physics or something because it's really reliable. If you enjoyed this video or found it useful, give it a like and maybe consider supporting the channel over on Patreon. Patrons can download files for all of my projects and get a little peek behind the scenes. Thank you for watching.